Everyone, welcome to another episode of A Little More. A Little More was established in the fall of 2020 as a platform to gather academics, Iranian academics in different disciplines, to encourage dialogue in an interdisciplinary manner, to also encourage us to learn more about different fields. Today, we are honored to host Professor Cumrun Vafa for our first in-person meeting of this series. Professor Vafa was born in Iran, and then he moved to the US after attending Abdus High School. He did his undergrad at MIT, and he received a bachelor's degree in mathematics and physics. And then he went to Princeton in 1981 to pursue a Ph.D. in physics. And he has been at Harvard since then. He's now a Hollis Professor of Mathematics and Physics at the Department of Physics at Harvard. And his main research interests include are around string theory. And please welcome me in. Please join me in welcoming Professor Vafa for our talk today.
Thank you. Thank you very much. Pleasure to speak for this audience and more broadly the Iranian community. I think you guys are the future generation and the hope of the Iranian, I would say, people in general, regardless of where you are. And so I made sure that I make time to come and participate in your program because I think it's one of the most important things to for the hope of the future for Iranians. It's a little bit awkward to be speaking in English because I think almost all of you, well, all of you seem to be, at least the ones I heard, speak far better than I do. So, so I think anyhow, I will go with English, but at the end, maybe questions will be in Farsi if that's okay with everybody. So this is going to be a relatively short talk, I think. We'll see, so that there will be room for questions and answers and so on at the end. So I will be going relatively quickly. And my hope here, my aim here is to give you just a flavor of what's going on in fundamental physics and what is string theory. And this is going to be really a very quick introduction. Maybe I should first get an understanding of how many of you are graduate students. Is everybody a graduate student here? Who's not a graduate student? Oh, okay. So majority are undergrads. Okay. And how many of you are in science-related fields? Just oh, okay. So everybody is more or less the same. Most of you are science-related. Okay, very good. How many of you have heard about string theory? Okay, how many feel they know some more or less what string theory is? Okay. Okay, I'm glad that there are very few hands up. You could ask questions. I have something to say because this is what I'm going to say. It's rather elementary at the same time as trying to tell you what we have learned about string theory, which may be non-trivial, perhaps. So the introduction is I have to go back to the basic pillars of modern physics. What is modern physics telling us? Well, we are trying to understand how everything is made up. Well, things are made of matter, and there are forces between them. So the basic pillars of modern physics is understanding forces and matter, and we think they're both made of particles. Both matter and the forces are made of particles. So that's the fundamental point that we have to bear in mind. So for example, here, this is a diagram that you can see an electron, which I denoted by E, and then there's another electron with the E, they are moving, and one of them sends a photon denoted by gamma to the other guy, and the other electron absorbs it and moves on. So what does this do? Well, this causes electric repulsion between electrons. So the act of electric force is given by the exchange of photons between electrons. So photon is a carrier of force, electron is a matter. So, but both are given by particles. So this is the kind of an example we have in mind. Another example, more fancy, is here is a diagram for weak interaction. So here you see the particle, which in turn decays to an antineutrino and an electron. And this is a weak interaction here. And here between quarks, there's another force, which is the strong force, and they are exchange of gluons. So I just showed you all the three forces which are not gravitational. One is electromagnetic, That's the first slide. The weak interaction, which gives you radioactivity, and the strong force, which is the force between the quarks in the nucleus of the F. Okay, so that's the forces that matter. They're all made of particles. The next pillar of modern physics is quantum mechanics. Quantum mechanics is when we want to talk about microscale, small scale things. Things are fuzzy. Things are a bit fuzzy. And the fuzziness is very important in understanding the physics. There's some uncertainty where things are. Things are like moving around in some way, which make things a bit more fuzzy. For example, if you look at the atomic, the electrons in an atom, they form, they have a cloud around the nucleus, and the electronic cloud is given by some beautiful configurations here depicted by these pictures here. And basically means that there's some fuzziness of where the electron is. And where the electron is and how this fuzziness is the subject of quantum mechanics. This fuzziness at big scales, like the scale we see each other, it looks not there. It looks like we don't have any fuzziness here. And when you zoom in, you go close to the objects and go to the atomic scale and smaller, the fuzziness becomes more and more important. This quantum mechanics is important. Okay, so that's the other pillar of modern physics. Here's more fancy pictures of this lattices and so on, where you can see that this is from a Farsi one, so you can practice your Farsi if you want. And finally, the third one is Einstein's general theory of relativity. And so this is when you want to talk about the macro scale, like planets, you want to talk about galaxies, the whole size of the whole universe, and all that. And when you're talking about macro scales, big scales, gravity dominates everything. And Einstein's theory of relativity is what describes the gravity, the gravitational force. And so Einstein's theory explains how the gravitational force is described by geometry of space and time, by curvature and pull and push of the point in space and time. The distances change, and that is a way to geometrize and understand gravity using Einstein's theory. And this is a depiction of that. For example, if you have an object like a star, it curves the fabric of space and time so that things stretch or contract. And when, for example, an object moves around them, even if it wants to go straight, because of that curvature, it kind of bends. And this is kind of the bending that we see like gravitational force. So we interpret it like a pull, like Newtonian mechanics would say, well, you're pulling the object by gravitational force. Whereas in this Einstein's description is geometric, completely geometric. And so this we know is the correct description of gravity at large distances. It even applies, as I said, to the collection of galaxies and the whole universe as a whole. So it's quite remarkably successful. Okay, so I told you about the three pillars of modern physics. Well, it turns out that these three things cannot all be right, that they lead to inconsistencies. If you believe all three, and if you try to work and understand what consequences there is, you find it doesn't work. You get inconsistencies, contradictions. Okay, so which one is false? At least one of them is false. And it turns out, indeed, the first assumption is false. So fundamental entities are not made of particles, but made of extended objects like strings. So what is strings? Well, so strings, or more, which is the cornerstone of string theory, is a theory which has been pursued for over 50 years as a candidate for fundamental theory of everything. And it's the most promising candidate which we know today, unifying Einstein's theory of relativity and quantum mechanics. So this contradiction between gravity at large distance and physics at small distance given by quantum mechanics gets resolved when you take into account this extended nature of particles being like loop-like. So, so this basically it's kind of like a particle like quark is indeed like this loop of string. So when you zoom in, so here going the arrow is showing what happens if you go closer and closer to the quark. You will not see a point, you will see some extended structure like a string, like a loop of energy. So, but the distance in which you have to zoom in, you might say, how close do I have to go to the quark to see the size of this little loop? 10 to the minus 30 centimeters. And to give you a scale, the size of an atom is 10 to the minus 8 centimeters. So this is 10 to the 22 times smaller than the atom. So we're talking about fantastically tiny, tiny, tiny scales. And the interaction between strings is a nice geometric interaction. You have two loops, like strings, they move around, they join, and they become one string, or one string splits to two strings. So that's the interaction between strings. So all the interactions, electric forces, strong forces, weak forces, all of them are obtained by strings emitting and absorbing. It's that simple. So all these complicated rules and all that is nothing but strings being absorbed and emitted in this form. In fact, it unifies all the particles into string excitation. So it's only one particle, meaning it's one string, but string can have different excitations, oscillations, or wrapped around different things. And this gives you the unification also of particles and forces into one object. So it's aesthetically pleasing. It's just one object, unifies all of them. And interactions are geometric. It's just like the two things come together and form one thing. And by the way, this is called a pair of pants diagram because it looks like a pair of pants. Nothing very poetic or whatever, but then that's what they call it. It's just funny terminology sometimes. Now, unfortunately, it's too early to present the final formulation of string theory. I wish I could say, well, these are the analog of Maxwell's equations or string theory or whatever. It's the Newton's laws, and I'll write it down, and then I'll tell you. We are not there. Despite the fact that we have been working on this 50 years, not me, of course, alone, because I was a kid then, but then, yeah, the community of physicists have been working on this subject for 50 years, but it's still a work in progress. So it's not a trivial thing. And part of the reason, in fact, the main reason is that string is tiny, and therefore it's difficult to see in experiments. In fact, in today's experiments, it's impossible. We don't have enough resolution in the experiments to be able to resolve that small distance case. So therefore, we do not have direct detection of string theory. So string theory is a theory right now, not proven by experiments, which puts us in a slightly awkward position, because in science we want experiments to confirm our theory, and we're not there yet. So how do we know that this theory is a good theory? We don't have experiments. That worries us. And I would say that the main reason we believe this is the correct theory is its mathematical consistency and resolution of contradictions between quantum mechanics and Einstein's theory. Since both quantum mechanics and Einstein's theory should be there, and this finds a beautiful resolution of that puzzle, we believe it's true. But we have not detected it, and that's a tough thing. So I already told you about the size of a string being very tiny. In fact, even though today in experiments we do high energy experiments, in Geneva, for example, in the Large Hadron Collider, we have a huge amount of energy. Even that energy is too little compared to the energy we need to probe the size of the string. In other words, when you shoot two particles together, if the energy is sufficiently high, you can get them close together and see the small distances. But the energies at the Large Hadron Collider in Geneva, for example, is a trillion times or so or more. It's too small to be able to see the string from there. You cannot excite the vibration modes of strings to see it as objects like strings excite them. So that's hard to do. So it turns out that even the incomplete knowledge we have of string theory nevertheless conveys important new lessons about our universe. And it leads to many new principles which are counterintuitive. It revolutionizes our understanding of space, time, and everything around us. So we have learned, even though we are far from finishing it, we have learned quite a bit, and it really changes, it's mind-boggling and changes our view of how the universe works. So what I'm planning to do here is to give you some of these counterintuitive new principles that are emerging in string theory that we're sure about. And I want to explain how do we know them and why we're sure about them. Perhaps the most important lesson we have learned in string theory, and that's kind of a general summary of a lot of these connections I'm going to tell you about is what's called duality, string duality. And what is duality? Well, duality is a general phenomenon that two very different looking things can nevertheless be the same. And the reason they look so different is that it's like you have dialed a parameter and you go from one regime to another. It's like two pictures morphing together, one from one to the other, very smoothly. So we think that all of physics is in some sense morphable to any other one. And understanding how this works and how they go from one to the other is the subject of duality, understanding that feature. So things which look totally different are nevertheless can be related, and that's quite remarkable. It is perhaps captured by this beautiful drawing of Escher of day and night. You see, if you look at this drawing and somebody asks you, what is this a drawing of? You might say, well, you know, it's a blackbird flying on the day to the left. And someone said, no, it's not the day, it's night. And it's not a blackbird, but whitebird flying to the right. And somebody would say, no, it's actually the fields they're talking about, the black and white fields and so on. So everybody would say differently. And they're all talking about the same drawing. And they're connectable. So here, this is the kind of thing I mean when I talk about duality. So the left to right is a duality to day and night. And in this transformation, day goes to night and the white bird goes to blackbird. Sorry, white bird goes to the white sky, and the black bird goes to the dark sky. So there's this kind of transformation happening. And similarly, from up to down, you can see what the transformation is. So this is something you can bear in mind when I'm talking about duality, this kind of transformation. Okay. So these corners are typically the things which are easier to describe. In the middle, it's harder to say what is day, night, whatnot, bird, etc. It's a mixture of all of them. It's much harder to understand. So typically, you can think about these corners of this Escher's drawing as corners of parameters in physical theories. As we take the parameters like the constants in your theory to large values, this one, that one, you get simple picture at the extreme values. But in the middle, you find complications. Okay, so now I'm ready to get to some of the examples of some of the things we have learned. Basics of space. We all know what space is, right? You know, 1, 2, 3 dimensions, x, y, z coordinates, we're familiar. So what are we going to learn from that, from string theory? Is the dimension of space and time 3 plus 1? Do we have 3 spatial dimensions and 1 time? Well, that's the first thing that the string theory seems to say no. The dimension of space and time is not 3 plus 1, despite what we thought. Hard to believe because we look around, it's 3 space, right? I mean, that's clear. And time, we can just look at time. It rolls forward. So we have 3 plus 1, but nevertheless, string theory says that's incorrect. And how could it be incorrect? It is because string theory predicts extra dimensions which are spatial. So like x, y, and z, there are other x, y, z's. X prime, y prime, z prime, etc. A few more. And how could it be that we don't know about those coordinates or we didn't have to deal with them before? Well, the reason is that we believe these are tiny directions. So this tiny part of the space like that. And to imagine it, imagine like you have a geometry like this, where these extra dimensions, d dimensions, whatever they are, they're like tiny loops, tiny spheres or tiny circles, which when you look from far away, they look like a point. But when you come close to it, it looks like, you know, there's actually a circumference. So just like that, we believe that in our universe, the macroscopic universe, you can see only 3 big dimensions, but they're tiny curled up dimensions. They're harder to see by experiments, and that's one thing which we will have to deal with. It's somewhat like this picture. Well, you see the ants here. The ants going on this rope. You might think that this rope is one-dimensional, but actually, from the perspective of the ants living on it, it certainly looks more than one dimensional. They go around and so on. So it depends on how fine we want to zoom in. So zooming in this language translates to higher and higher energies in experiments. So with higher energies, we should be able to see these extra dimensions. Is the dimension of space and time well defined? So I told you it's not 3 plus 1. Then you can say, okay, what is it? Is it a well defined question? Can we say what it is once and for all? The answer is no. We cannot even say what is the dimension of space-time. It's not a well-defined concept. It depends on which duality frame we look at, in other words, which corner we are at. In one corner, it could be 10-dimensional. In another corner, it could be 11-dimensional. In some other corner, it could be 9-dimensional, and they morph to each other. So to say what is the dimension of it depends on which corner you want to be. It's like in that Escher drawing. In one corner, you could say, oh yeah, it looks 10-dimensional. They all say, no, no, it's 400, it's 9-dimensional. And then someone in the middle says, no, this doesn't look like space to me. You cannot count dimensions. So the notion of dimension is not an invariant concept. In corners, in parameter space, it becomes well defined. So sorry, I forgot to explain the picture here. So here, for example, you could say it's 10-dimensional, but there could be a parameter which, when you increase it, you can see a circle popping out and getting bigger and bigger. So that parameter, changing the parameter, like call it G here, can make it bigger and bigger, and you get a bigger radius, and that becomes 11-dimensional. So what's the actual dimension depends on which parameters you have in your theory, what values you have put them. So, and moreover, I said string is like one-dimensional object, but actually, is it one-dimensional? Not necessarily. What happens is that if the dimension of space extends, like you have one other dimension behind it, then the string can also become a membrane. Just wrapping like that. So the string can also be viewed as, in some cases, like a membrane or even higher dimensional objects. So the main lesson of string theory is not that everything is made of one-dimensional objects, but as extended objects, which could be membranes or higher dimensional objects, not just zero-dimensional point particles. Is the topology of space an invariant concept? Can we actually say what is the topology of space? Now, some of you may not even know what do I mean by topology of space. So what does topology mean? Topology of a space is a mathematical notion of a property of a space. Like if you have, for example, a surface, you could say how many holes does it have? Holes or handles does it have? Like if you have a pretzel, you can let me count how many holes does it have and so on. That's called its topology. What is the details of the shape and all that will be much more refined property of that, which we call this geometry. I'm talking about topology, which is a crude characterization of the space. Like a ball has no holes, but you can squeeze it and stretch it. That doesn't change the fact that it has no holes. So you can ask, can we say something? I'm saying there's extra dimensions, and you can go to one duality corner and ask, can we ask what is the number of holes of that space? Can we say what are the topological properties of that space? Can we characterize it? Turns out the answer is no. You cannot even say how many holes it has, because it turns out things which have, let's say, 3 holes and things which have 1 hole, they can be equivalent. So the notion of topology is even difficult. It's not an invariant concept. So the duality maps them from one to the other depending on what kind of parameters we have. These are called mirror pairs. Mathematicians were shocked when physicists claimed that there is this symmetry, which we call mirror symmetry, because they said, look, topology of a space is sacred. That's the thing you don't touch. It's the basic of a space. And if they are different between two spaces, the spaces are different. It cannot be the same. And physicists strictly said, no, they could never just behave the same way for physics. And the way physicists managed to convince mathematicians about this is that they use these symmetries to derive mathematical consequences of them, which mathematicians didn't know how to compute before. for example, counting how many spheres fit in certain spaces. We use these kind of symmetries to predict these numbers, precise numbers, which were interesting to mathematicians, but was difficult for them to calculate. And so once they found that, this symmetry predicts how you can calculate them, they began to take it seriously. So from physics, they have learned properties about mathematics, which is interesting for pure mathematicians to try to understand. So that's why mathematicians are super interested also in string theory. Is the diameter of a space an invariant concept? Can you say, for example, what is the distance from that wall to this wall over here? Or if you have a circle, can you say what is the circumference of the circle? You would think, yeah, why not? For example, if you take a circumference of a circle, let's say circumference is r, usually we say 2 pi r, but here that's just denoted by r. And suppose the speed of light is c, then we can send the light around and measure how long it takes for the light to come back. And if the time it takes is t, you multiply the speed with the time, you get the distance it went around, and that's the circumference. It will be c times t. Seems well defined. We can do an experiment and find it. What's the problem? So Einstein would have said there's no problem defining the diameter of a space or circumference of the circle, just by sending the light around. But string theory says not too fast. The diameter of the space is not an invariant concept either. It turns out there's a symmetry, duality in string theory, which inverts the large space to a small space. What we call the length inversion. So a space of circumference r could be equivalent to a space of a circle of circumference 1 over r. Inverted, where I'm using the units of string. So at units of string, which is 10 to the minus 30 centimeters or so, that's what I mean by 1. So that's like the self-dual one. But otherwise, if you go 10 times bigger than that, it's equivalent to a space 1/10 of it, and so on. That is bizarre. How could that be? I mean, we can see by our eyes. It's very different from a small one. What does that mean? How could it possibly be? Einstein would say, well, you send the light and measure it. What do you mean? There's an unambiguous measurement of time it takes. Well, the problem is if Einstein raises objection, the answer is that while Einstein talks about these waves to send around, there is another kind of a wave we can make using strings which are wrapped around the circle on the other one. And they form a new kind of light. So if you send this kind of light around the space, you measure the radius is r. But if you send the other kind, you see that the radius is actually 1 over r. The time you get is different. So there are two kinds of lights. And so that's why you get two different answers in this case. So this kind of symmetry is really mind-boggling, and it is kind of showing us that this thing is far more non-trivial. So our whole notion of geometry, topology, and all that is being changed. So, for example, you have all heard about Big Bang, right? Big Bang means that you have the universe, which is beginning of it is maybe a point or very small at least, and then it starts expanding. So if you take our universe and go back in time, shrink, you go close to the beginning of the time that the universe was there. So this is, if you denote this by time axis and the radius we are growing, the blue one, the blue curve. If you go back down, you find that the radius is shrinking as you go back towards the Big Bang. But I told you that there's a symmetry, r goes to 1 over r. So at some point, even though our universe will be shrinking, it's equivalent to a dual universe expanding. So you get smaller and smaller, but when you're getting smaller than the string size itself, it is equivalent to expanding. It's not like you're bouncing, but I'm just saying, even if you continue going smaller, it's better or easier to describe the same universe as if it's expanding in terms of these other variables. So there's this symmetry that we have to deal with. So this suggests that maybe there was this other universe description which was coming to this duality symmetry. So for example, this is the way we denote the geometry of the Big Bang. The radius of the universe is expanding. In the dual picture, it would be the opposite. That what we are thinking of actually expanding is contracting and vice versa. What are black holes made of? Well, black holes have been observed. It's one of the most enigmatic objects in the universe that attracts the attention of everybody, starting from children all the way to adults, and everybody is interested in these enigmatic objects. Everything which falls in it is doomed to be staying there. And what is it made of? Well, it's made of things which fall into it. But except that when you solve Einstein's equation, you find that there's exactly a unique solution to a black hole, which suggests that there's only one possible degree of freedom on it. And that's inconsistent with the fact that you can throw all these different kinds of things in it. And somehow when you throw it in the black hole erases the information of what you threw in, which sounds strange. So Hawking found that that's actually so strange that it's not true, and that there should be some degrees of freedom that the black hole is made of. And so, so as I said, Einstein's equation gives you a unique one, but Hawking suggested that no, there should be some stuff that the black hole is made of, and the degrees of freedom of the black hole is not just one, but a huge number, which is given by exponential of the area of the sphere, or what's called the horizon of the black hole. Horizon of the black hole is the place where if you go any closer, you will not be able to return. So it's the last point where you can return. It's called the horizon of the black hole. So the area of that, exponential of the area of that over 4 denotes the number of degrees of freedom of the black hole, where you measure the area with the fundamental Planck units. And this, the fact that the degrees of freedom goes like the area, related to area instead of the volume, is a feature which is often referred to as holography, because it should be, usually the degrees of freedom goes like volume, not like area. So this is like a holograph in some sense, and this is called holography. So the main question in the context of black hole is, what is it made of? Where are they hidden? And again, string theory gives an answer to this question in an elegant way. The black holes can be obtained in string theory as wrapped strings or membranes, or what we generally call brains, in the internal dimension. So if you take extra strings, circles, and so on, you can take a circle, a string, and so on, wrapping around these circles, and they look like particles from our perspective. Namely, above this point, there's this compact space. These are the curved up dimension I was talking about. And you can take a string wrapped around one of these circumferences and give you a particle. If the string wraps more and more and more, or goes with zigzag path and all that, the mass of the object gets more and more, because you have to stretch it more and more. It's longer and longer, so it gives you more and more energy. So you can create a big black hole by taking one of these strings or membranes, wrapping around different cycles and going crazy. From the perspective of the macroscopic space down here, you just see a black hole. It seems like there's no degree of freedom, it's just one. But the extra dimensions of string theory give you these extra degrees of freedom that Hawking was predicting. But now we can actually count them by just counting how many ways these strings can wrap around, or membranes can wrap around these extra dimensions, and we get, lo and behold, the exact prediction that Hawking had, which goes like exponential of a over 4. Is universe unique? Are we unique? Well, the word universe sounds kind of like, by definition, unique. Well, what do I mean by unique? I mean, could you conceive of other universes other than ours? That's what I mean. Could there be other universes that are perfectly fine and we are not in it, for example? Is our universe the only one? The answer seems to be a resolute no. We now believe that there are perfectly consistent other universes with perfectly fine physics. What do I mean by other? Well, these other universes may have different number of particles or different strings and so on, and different forces around. Totally different properties. Number of macroscopic dimensions may not be 3, may be different, no problem. So this we have we have learned that there are perfectly consistent solutions to string theory, which is not our universe. In fact, it's worse. Our universe is very hard to get in string theory, and these other ones are much easier to describe. String landscape, what we call string landscape, is the solutions to string theory, the space of all possible universes that can exist, consistent with string theory. And we know there's a vast space, and our universe is one of them, presumably, but we live in a very exceptional corner with very special properties, but still, it's just one in a many, many possible would-be universes. Will the universe last forever? And the answer is that our universe will not last forever. Our universe is doomed, and we're going to go away. Now, I don't mean go away in a very peaceful, necessary way. I mean just disappear. Now, it might be hard to say, what do you mean by disappear? Disappearing of the universe would look like. Well, it doesn't look very pretty, but let me try to explain how does it look. So, first of all, why do we know that, or why do we think that our universe is not going to last forever? The only solutions to string theory, there are solutions to string theory that last forever. There are universes that can last forever. We have found those. They are not our type. The universes that we have found that can last forever have a property called supersymmetry. This symmetry is an amazing symmetry which tells us for every particle, there's another particle similar in properties, but with a different spin. Like, for example, for electron, there will be another particle we call selectron, which has exactly the same electric charge, mass, everything as an electron, except it would be a spin 0 particle, unlike the electron, which has spin 1/2. And electron is a fermion, this other particle would be a boson. Terminology doesn't matter so much, but anyhow, the main point is that there's this doubling, so as if every particle should double. Those kind of universes where this doubling was there, they found examples of those which last forever. Our universe does not seem to have that property. There is no particle exactly like electron with exactly the same charge, except for a different spin. We know that because in experiments we would have seen it otherwise. By these colliders, they would have created these other particles. They haven't, therefore they don't exist. At least, even if they are there, they don't have exactly the same mass as the electron, and in which case it would mean that our universe does not realize the symmetry. At best, it's what we call spontaneously broken symmetry. So supersymmetry is not a property of our universe. And so this raises the question, how long do we have? Well, we are not sure. Preliminary estimates suggest that we can get to our dinner, but no, I'm just kidding. Preliminary estimates suggest that the time scale could be anywhere from now to the trillion years. This is just estimates. Just for your scale, the scale of our universe now is about the age of our universe is like 14 billion years. So it could last maybe a factor of 10, 100 more, maybe. Now you might ask, how would it end? How would what's the Tesla line on its point? There are different mechanisms of how it might go away, but I'll just tell you one possible mechanism is the following. You're looking at the universe. At some point, there is a small bubble of a new universe created in some distant galaxy, some new universe. And you see this universe, this bubble, this new universe with new properties, new particles emerges, and it moves with the speed of light. It's moving with the speed of light, and it overtakes our universe and converts everything we are to this new universe. And so you say, how would we know? You can look at telescopes. No, it's moving with the speed of light, this bubble. So therefore, as soon as, before you detect it, you disappear. So therefore, it's going to be presumably painless. I don't know, but then yeah, it just erases everything, and it replaces with a totally new universe. And that's the end of my talk. Thank you. I guess, and I'll be happy to take any questions or any questions, first of all, related to this or not related to this. But not related to politics, related to science or the topic. Yes.
All right, so
If I'm being cautious, so after that.
I'll just say it in English. Okay, I don't think I can say the question first.
Oh, you prefer English. So anybody who prefers English, please stick to English. Yes, go ahead.
So I was wondering if, like, so you're talking about the duality, right? That like string theory comments on like, oh, you have like the radius, and then you have like 1 over r,
Yes.
having it the same time,
Yes.
right?
Yes.
So does that in any way explain the wave particle duality of light, let's say?
Talk about particle wave duality. Is that the same kind of block as I'm talking about? We don't think so, but may well end up being like that. So at this point, the answer is no. We think that's not the case, but who knows? It's conceivable that deeper understanding of quantum mechanics might tell us that particle wave duality is similar to ours. But as of now, we don't think of that as the same kind of block as I'm talking
I have another question.
about. Go ahead.
So you know how you said like black holes, the way that string theory would like solve them is that it like as we see it, it's like something like a one-dimensional plane. Whereas like if it's string theory related, you had that image of like the flat, plane, and then above it was that like donut pretty much. Just like how like you were showing like, oh, that line can, with some kind of G force or something, like the force is called G.
No, I do as a parameter.
Yeah, parameter. Parameter can become like,
Change the radius,
to
right.
change the radius and then you get a new dimension, right? So I read that like the whole point of a black hole is that it's pretty much like a particle that is like so dense that like it attracts everything to it. It's because like there's like a certain radius that like makes it so it's like anything can be a black hole as long as you shrink it to that radius.
Right.
So does that mean that like we could only see those like newer dimensions if like matter was shrunken to that radius that like makes a black hole?
Well, we have black holes, but we can't see these extra dimensions. We have people that have taken a picture of black holes, you know that, right?
Yeah.
But we simply cannot see the extra dimensions, so that doesn't solve that problem, unfortunately. But to describe the properties of the black hole, like counting degrees of freedom, it turns out that we simply need extra dimensions, extra degrees of freedom. So, how many people find black holes mysterious? Yeah, they're mysterious. How many of you feel you don't understand why nothing can come out of it? So, most of you. So let me explain why that's not that mysterious. So let me explain why you should say, oh, that's not. So you all have heard about if you throw something up in the air, whatever goes up comes down. But that's not true. Because there's a thing called escape velocity. Have you heard about the escape velocity? There's a velocity that if you take a rocket and let it go with that speed or higher, to get out of the Earth orbit and never come back. So it just goes out. Escapes the velocity, escapes the Earth orbit. So that's not that strange. And that can actually calculate using Newtonian mechanics to get the exact value and so on. So no problem. Now, this is the Earth. So this is the Earth. So there's a rocket and you calculate the escape velocity. You get some number that just call it whatever it is. 10 kilometers per second, whatever it is. Next question is, suppose we add more mass to the Earth without changing its size. Just take this Earth the same size, just stuff in some extra matter inside the Earth. More mass of Earth. Rocket is there. You want to send rocket up. Do you think the escape velocity goes up or down or doesn't change? It goes up. Why? Because there's more gravity. You have to get a higher kick to get it out. Okay, put more matter. What's going to happen to escape velocity? Up, up. The more matter you put, the higher it goes. So when you put so much matter that the speed that you need to go at escape velocity is bigger than the speed of light. There's nothing higher than the speed of light. So nothing can escape. That's it. That's black holes. So once you get to that situation where the escape velocity is the speed of light, you've got black holes. Nothing amazing. That's it. So even the Earth can become a black hole if you put stuff in a lot of stuff in it. Or another thing you can make to make a black hole is to shrink something. Because it turns out if the radius was smaller with the same amount of mass inside, the escape velocity goes up. So if you take, for example, the sun and squeeze all the mass inside the sun to about, I don't know, a mile or 2 miles, it becomes a black hole. So that's black holes are that kind of object. It's not that mysterious to create that. That's why we have black holes in our universe. In fact, we believe at the center of every galaxy, there's a supermassive, humongous black hole, including our own galaxy. So they are very typical. They seem to be seeds of our galaxies.
Are strings
in certain duality, in certain corners of the parameter space, yes. But there are other parameters where the strings are not there, but there are many parameters, for example. Different kind of corners. So as I said, the duality, which means that we can convert a string to a membrane to something else, does happen in string theory. Does that change? Smaller meaning what? Well, we have heard that particle theory cannot be consistent. That much meaning. So it cannot be particle. No. So the main ingredients cannot be just particle. That much meaning. Otherwise, we get contradictions. Good question. There are two types. They can be either looped or open-ended. So there are open strings and closed strings. We can have both types. Both exist. Yes.
And so you said like showed near symmetry in spaces, and so that would make like whatever. And then are there such weird like symmetry that actually bring how do you matter like whatever like
So I didn't completely catch your question. So if strings are moving in a space, when I talk about the symmetries of, I would say that if you take a space, the mirror of that space might have a different topology. So strings moving in this space or strings moving in that space, you might say, string says they are different. But string says, no, they're the same. Even the topologist might have said, no, they're very different. String says, no, there are other degrees of freedom shuffled around in such a way that they're equivalent physics. So it's very surprising from a mathematical viewpoint, and has led to new mathematical fields. So it's quite rich mathematically.
but to like strings have topology, does that like matter at all? Or I guess the shapes.
No, the string is nothing, no topology. The string is just the vibrating loop of energy.
So right now, duality somehow makes the general uncertainty principle.
Yes, who was asking that question? Particle wave duality.
Yeah,
yes. Yeah, he was also saying it's very similar, but we haven't connected it together. Yes.
So like, is it like any like you're talking like you're talking about the radius, which could be like number of r? Kind of reminds me of the like
yes. There's one element which is similar. It's actually the other way. So quantum mechanics tells you that the electron is not at one place but spread out. String theory takes it one further step. It says not only it's not spread out, but also it's not at a point it's spread out. So it's one more version of the equation uncertainty. So it extends that uncertainty. Yes, all I'm just saying is that when quantum mechanics says you have a point particle, and then but quantum mechanics says no, even though it's point, it's not at one point in space. It's spread around. String theory says no, not only that, but also each point that would have been a point is actually a loop. So it's the loop is spread around. So it's another layer of spreading away, making it more fuzzy. So one more layer of fuzziness.
So if string theory is consistent at like the level that it's studied at, let's say, right?
Yes.
And like you would say that string theory is a fundamental that can describe not only our universe but other universes.
Yes.
Does that mean it is possible or it's not possible that other universes have different laws of physics?
They do have different laws of physics, that we know. But depends on what you mean by laws of physics. But if you mean by laws of physics, like forces, different matter, and so on, yes, they're different. But if you mean that the general principles of quantum gravity are different, no, I'm not saying that. They're the same principles of physics, but different manifestations of those principles. A quantum gravity could have, you know, like electron, or some electron could have completely different particle, completely different forces. That's what I mean.
So if the laws of string theory at its most fundamental level then are consistent, then how do they confer those different laws at the more like macroscopic level in other universes?
Okay, so in string theory, we expect that any other universe can be accessible in our universe now. That is, we can create a bubble in principle in our universe, which is the bubble of any other universe that we may wish to visit. So in principle, there is nothing that separates us from other universes. It's just that we don't live in them. But there's nothing in principle problem that we cannot have. So it's not like we are inaccessible to other universes somewhere nowhere near us. We can create them. So in that sense, you could say, well, there's then again one universe because we can create everything else within ours. That's a matter of terminology. How do I what? How do I go about creating it? Good question. We don't know. So presumably it's not going to be easy. Namely, presumably has a huge amount of energy involved in it. I would expect that's one obstacle. So we know theoretically it should be possible, because if you do it, we get contradictions in quantum gravity. So we know that that should be possible. With finite energy, it should be able to, not infinite energy, finite. But how much exactly, what we do, we don't know.
You said that we have like 9 and those are all spatial dimensions.
Yes.
Is there, I guess, not?
Well, people have thought, if I myself worked on versions of string theory just 2 times, but I think that those are not connected to the other group, which is only 1 time. So it seems like the 1-time kind of universes form a close set among themselves, and we think we are in one of those.
Is the shortest idea like any force related to that?
The Schrödinger's cat is what?
Like the Schrödinger's cat's many words, like
Many word.
is it?
So there's a many word interpretation of quantum mechanics. That's just a way of interpreting quantum mechanics. And that you can still do that in string theory context either. So string theory and quantum mechanics are orthogonal in the sense that we are not changing the rules of quantum mechanics, the same rules. So you can interpret it usually many word interpretation of quantum mechanics or whatnot. Quantum mechanics is still very enigmatic in my view. I think that we have not set up on a deep understanding of quantum mechanics. And it may very, very well be related to the dualities, understanding this wave part of the duality in a deeper sense. In the same sense as we have understood the rest of the duality. It smells like it should be possible, but we haven't managed. Yes?
Can we use hadron collider to create those bubbles?
In principle, if you had the huge energies, yes, but the problems that are colliders, and that would be one way I would go about engineering them if I had enough energy. If you have enough energy, you can in principle imagine huge energy to create such problems. But not the energies that see the large hadron collider.
So what do you know about the magnetic field that is on the aerospace? For example, like Bermuda Triangle, that some people disappeared on them. So do you think can they be like a black hole or something?
No, I don't think so. I think it's very romantic. I remember when I was movies about the Bermuda Triangle, so I sympathize with the question, but I don't think they are. At least that's not the way, but who knows? Yes.
Have you invented new mathematics?
We are inventing more than one new mathematics. So but it's a process, it's not finished. So just like Newton had to invent calculus to figure out the stuff, he was done. Once he did calculus, he was done. Not us. So we have already, I think, a few branches of mathematics have been revolutionized by string theory, and we're still not there. We're still not on string theory enough. But I would say that mathematicians are super interested in string theory because of the connection. Not just one area of mathematics, many areas of mathematics are being unified using string theory. So it's actually quite quite an interesting interaction. Mathematicians, there are many areas: number theory, algebraic geometry, topology, group theory, and you have mathematicians focus on one or the other because they're very compartmentalized in some form. So what the beauty of string theory is that it actually utilizes all of them in some form, and so it combines them and connects different math together. So it actually is quite remarkable, rich math, and that's one of the reasons we think there's some truth to it, because no human being is smart enough to have come up with such a structure. It's something quite rich. Yes.
You mentioned that you've conducted some experiments to show that there are forever lasting universes, right?
That there are what?
There are forever lasting universes, right? And this universe is not lasting; it's not going to last forever. So
I didn't carry out experiments. I said our theories predict.
oh, so this is just theory, right?
Our theory predicts.
Got it.
Yes, but that's not experiment. We should put experiment. I can do this. No, unfortunately, I can't do that. I wish I could have go to that. Maybe not actually. Actually, I'm not sure of that. It's good. Well, I think that the notion of how you define a creative is difficult.
Well,
It's not like me and you, for example. Like, it's not like fashion.
Well, like, the question I'm asking is like, from what I've read, I saw that like quantum physics, the calculations become really almost impossible to prove that what happened before the
Well, I was saying, for example, the different duality, and you get the two pictures of the bird. I think I personally try to separate the discussion between science and religion.
Yeah.
And part of that, I will tell you why. It's not like, first of all, I was controversy, that's for sure. But even forget about that. The people, when they talk about religion, they have very specific views, and it may not be the view you and I have on what they're on. So if you try to say, does A exist or does A be this or that? If you say yes or no, you're assuming that you have the same common definitions. That may not be. So, for example, I will tell you, in my view, every scientist is religious, even though they may call themselves atheists. But now you might not wait, that's contradiction. Doesn't make sense. But what do I mean? Because my definition of religion is different from maybe other ones. And for me, the definition of religion would be things you don't have a rational evidence for, but you believe it. If you believe it's true, and you cannot convince them. In some sense, scientists believe there's some layer of something there they're trying to find. They don't have a proof that it should be there. But they're looking for it. So there's irrational belief. Or in science, we have an irrational belief in simplicity. People say, scientists are very rational, they have sat down, and things are simple because of past experience. Not really. I think we have this gut feeling that this got to be simple. Why? It's a religious belief. So I mean, to me, this people try to distinguish science and religion in some form and so on, but it depends on what you mean by religion. So I usually don't go in those directions because it's very confusing.
Speaking of religion, string theory is definitely, by your definition, of religion because it hasn't been proven yet. What is the likelihood, in your opinion, that string theory turns out to be wrong?
0. That's a religious statement too. A strong belief. I find that what I think could happen is that what we mean by string theory might get defined. In fact, many of the things I told you, if somebody had told me 20 years ago, I would have said this is not string theory. Because many of them is the evolution of what I would have called string theory 20 years ago. So I could imagine our understanding, in fact, presumably this would happen, it will evolve to what I would still call string theory. For example, as I told you, strings could be membranes, but we still call it string theory. So terminology is from the previous era. But now we know there are other extended objects in that theory, which are membranes. We didn't know about these membrane objects before. So yes, so we can evolve and understand more. That I think most likely will happen. But I still think that we are closer to the truth in this context. It's not like totally different direction. It's this direction. Yes.
اولین نکته شروع کردن با این پروگرام تئوری
string theory شروع شد چه یعنی چه شروع شد یعنی پر کردن
تصادفی بود
یعنی پر کردن فاصله بین اختلافی که بین relativity داشت و
یه نفر سوال خیلی خوبی بعد این توضیح دادم. توی شروع کرده بودن در دهه اواخر 1960 داشتن آزمایش می‌کردن توی همین اکسلراتور با نشستم پایین‌تر حساب داشتن چیزی حساب کردن دیدن که یه خاصیت داره این تعارض داره که ذرات اگه اینجوری به هم برخورد کنن و اینجا بیان ذرات اینجا می‌گیریم. بعد دیدن که اگه نه اینوری هم بکنی یعنی ذرات اول میاد که ذره هم بدن اینا مساوی هم میشن مقدارش. اینو یعنی در یک آزمایش‌های همچین خاصیتایی دیدن که پس اول هم برسن اول هم نرسن هم این هم دیگه رفتار میکنن و این نفهمیدن چیه. یه نفر فیزیکدان به نام ونسیانو گفتش که من نمیدونم این چه خاصیت فیزیکی ممکنه اینو توجیه کنه. یه فرمول ریاضی نوشت. که احتمال این یعنی اینکه این پروسه انجام بشه رو به صورت یک فرمول ریاضی نوشت. گفت یه همچین معادله اگر توضیح بده این تعارض رو داره که این مساوی اون در میاد. فرمول یه فرمول ریاضی از اونایی که آشنا هستن از گاما فانکشن و این چیزا استفاده کرد و یک فرمول نوشت برای خودش. فیزیکدان خب این از کجا می رفتش به فیزیک چیه این فرمول ریاضیه. بعد دیدن که نگاه کردن که این چیزی که داریم میگی این یه ذره نداره، ذرات زیادی داره. برای هر عدد صحیح ذره داره درش. بعدن این شبیه oscillation استرینگ و خلاص شده ای بابا در استرینگ تری صحبت می‌کنیم. یعنی تصادفی. اصلا صحبت گراویتی نه، صحبت در واقع این بودش که این تعارض رو توجیه کنه. 60 سال بعدش در اواسط 1970 تازه شروع کردن صحبت کردن که یک ذره‌ای داره عین گراویتونه. یعنی همون خاصیتی داره که باید ذره‌ای که گراویتون داشته باشه که جاذبه نیروی گرانش رو منتقل میکنه داره توش. خب چه بسا داریم راجع به تئوری ذرات و گرانش صحبت می‌کنیم که اینا رو با هم ادغام کرد. اینجوری شروع شد. یعنی همش تصادفی پیدا شد. هیچ کی نمی‌خواد فکر کنه بگه من می‌خوام اینو حل کنم. خیلی تصادفی. کسایی هستن که ادعا میکنن به نظر من ادعاش درست نیست. مثلا لوپ کوانتوم گراویتی صحبت میکنه ولی اینا نسبتاً پریمیتیو است که حرفایی که صحبت داره درشون ولی چیزی قابل مقایسه با سیمتری نیست. مثلا 99% استرینگ تیوریستای فیزیک دارن استرینگ تیوری کار میکنن چیز دیگه. یه سوال دیگه هم هست اسمش تئوری استرینگ تیوری. مثلا 11 بودیشو میگن اف 10 بودیشو میگن استرینگ تیوری 12 بودیشو میگن اف تیوری. اسمای مختلف هست ولی همش یه طوری.
من اگر رسم بیادیم من دارم یه دایره یه پولی که مثلا شبیه شاید یه پول بیسیک
در تمام قسمت‌های ریاضیات تاثیر می‌ذاره. یعنی نظریه ریسمان الان وارد شده در تمام بخش‌های ریاضی به جورای مختلف و تراجکتوری مختلفش میگم نمی‌دونم چه اسمش هستش که الان در بودیم وارد شده در چیزای مثلا infinite dimensional نیکو وارد شده کسب می‌گردیم وارد شده در وارد شده مثلا این روز جان هم گفتم حساب کردن قرآن در فضای مختلف حساب کردن وارد شده همه قسمت‌های ریاضی حتی نامرگیری هم وارد شده مثلا چه جورای مختلف راجع به قسمت‌های مختلف ریاضی الان رسمی بذاریم
کتاب هست
کتاب‌های مختلفی هستن بستگی به هدف از اون کتاب هست. اگه برای پابلیک میگید کتابی هست که برای پابلیکه. اگه برای آندرگراد کتابی برای آندرگراد هست. کتابی هم هست برای گراد ریسرچ. آندرگراد کتابی بارتلز وی باکس نوشته. support undergraduate. Supporting that MIT desk by undergraduate. Now you shouldn't have theory on it. همین تمامی نداره. من خودم بهتون بگم که فیزیکدانای ما کار می‌کنن، ما خودمون شروع کردیم ریاضی، ولی به صورت کلاس نه. ما خوشبختانه همکارای ریاضی باشون کار می‌کنیم، مشترکین از اونها یاد گرفتیم. به این ترتیب با صحبت کردن باشه.
مثلا دوست در ریاضی مثلا برای دورانی کردن درس بیشتر
سوال سختیه. چیزای بیسیک رو باید بدونید در مثلا دیفرنشیال جیومتری که همه باید بدونن وقتی می‌خونن، نمی‌دونم چیزای دیگه شبیه الجبر جیومتری باید مثلا شدید رو باید بدونید، نمی‌دونم سخت چیز کردن، سخت که بگم چی نه باید بگید.
الان شما ریسنت‌ترین ریسرچتون تو چه زمینه‌ای از شکلی می‌کنه؟
الان کاری که من دارم می‌کنم اینه که خب من گفتم که ابعاد دیگه وجود دارن، شکل‌های مختلفی هستن. بعد این ابعاد چجوری فشرده کنید خیلی سوال سخت، نوع‌های مختلفی ممکنه باشه. هر جوری فشرده مختلف رو کنیم، فیزیک که میده در 4 بعد 3+1 فرق داره. تعداد ذرات فرق می‌کنه، جرش فرق می‌کنه، نیروها فرق می‌کنه. همین لنسکیپ که گفتم چیزای مختلفی میده. سوال اینه که آیا همه چی میتونیم بگیریم هر چی دلمون بخواد؟ چون بگیم من 5 تا الکترون می‌خوام، نیروها می‌خوام این باشه، آیا یعنی اوردر به قول معروف هر چی بخوایم مثل ملی بگیم من اینو رو می‌خوام. یه نفر میگه خب من فضا رو براتون درست می‌کنم اینو ببینید. جوابش اینه خیر. هر چی بخواید نمی‌تونید. سوالی که تو ملی چیا هستن؟ تو ملی که چی می‌تونید؟ چه ذرات، چه نیروهایی، چه خاصیتی چی؟ آیا ملی خیلی بزرگه؟ یعنی اگر کل ملی لیست غذاها رو بنویسید یا اینکه دنیا که میشه لیست بی‌نهایت بزرگه. ولی به نظر میاد تعداد اینایی که ما میتونیم از یک کوانتوم گرافیک دست بیاریم خیلی کمه. سوالی که چیا هستن؟ کدوما هستن؟ میتونیم بفهمیم کدوما هستن بدون اینکه اینا رو بسازیم فضا رو. به این ترتیب میتونیم درک عمیق‌تری بکنیم. اونایی که توی قابل قبول نیستن، توی ملی نیستن، در واقع بهش میگیم سوامپلن. یعنی تئوریایی که به درد نمی‌خوره. اونایی که توی جاهای وجود دارن میگم لندسکیپ. خاصیتایی که توی سوامپلن داشتن من دنبالش هستم. بهش میگن سوامپلن.
اگر سوال دیگه نیستش یه بار دیگه تشکر می‌کنیم. بازم ممنون که دعوت ما رو قبول کردین، خیلی لذت بردیم.